This video is an introduction to buffers. Buffers are solutions that resist a major change in pH. You can add hydrogen from a strong acid, you can add hydroxide from a strong base, and the pH only changes slightly. A buffer needs to have an acidic particle and a basic particle in order to do that. So you're usually going to find a weak acid and its conjugate base, or a weak base and its conjugate acid. Good examples might be some of these guys. Hydrofluoric is a weak acid. Its conjugate base is fluorine, so it could be any soluble fluorine compound. So like sodium will just be a spectator. The fluorine ion is the conjugate base of this weak acid. Another good example is ammonia. Ammonia being a weak base, the ammonium ion being its conjugate acid, and chlorine just a spectator. Chlorine and sodium won't have any effect on the pH. Another real common buffer is this acetic acid buffer, where you've got the weak acid, acetic acid, and then you've got its conjugate base, some kind of an acetate solution, sodium acetate being probably the most common. So let's look at adding acid to this buffer solution. If you add extra strong acid, which means like extra hydrogen ions, you've got this negative acetate ion. The negative acetate ion is attracted to this positive hydrogen, and instead of having free-floating hydrogen in your solution, which will have a major change in the pH, you actually form this weak acid. With a weak acid, we don't dissociate by much, so most of the hydrogen is going to be part of this neutral molecule, hydrogen acetate or acetic acid. So it's kind of a trade-off. Instead of extra free-floating hydrogen, which would kind of signify a strong acid, we'll trade that for a weak acid, something like acetic. So I should see less of a change in pH. Check out another example. Here's adding hydroxide, maybe from a strong base. If we have this acetic acid particle, well, this guy could lose a hydrogen to react with that hydroxide. And again, it's kind of a trade-off. Instead of having extra strong base ion, extra hydroxide floating around in the solution, you'll just form the conjugate base. You'll form some hydroxide, and the other particle formed will be water, or not hydroxide in this case, acetate ions. And the other product is water. So instead of, again, having extra strong base, we'll trade that for something that's weakly basic, like the acetate ion. Calculating the pH of a buffer is really simple. We're going to set up a basic ice table. Now, sometimes they're going to kind of ask you, like, what are the major particles in the solution or the major species in the solution? We've got acetic acid, which does not dissociate, so we're going to leave it together, and it doesn't dissociate extensively. So we're going to consider this one particle, O2. Sodium acetate, just a salt, so this should dissociate. We'd have sodium ions, we'd have acetate ions, and there's always water. Of these, we've got a spectator, sodium. Sodium's not going to be part of the reaction. Sodium really can't affect the pH. It can't produce hydrogen. It can't pick up hydrogen. So there's our spectator. This is considered an acidic buffer solution. So we want to try to write an equation that uses whatever particles we've got left. So again, you could kind of write this a few different ways. I like to put the water in. You don't need to put the water in. So you could write this either way, an acidic buffer solution. If you didn't put the water in, you'd have something that kind of looks like this. The hydrogen acetate has a tendency to dissociate a little bit into hydrogen ions and acetate ions. Or, I don't know, with weak acids and weak bases, I kind of like to put the water in. you could write it like this. O2 plus water. We're going to remove this hydrogen. That's a goofy looking hydrogen. We'll be left with the acetate ion and H3O, like a hydronium. I mean, the hydrogen, hydronium, numerically it's going to be the same value, so it really doesn't matter how you want to write your equation. All right, we're going to set up an ice table. ICE. We're going to start with what we have. We have 0.5 molar acetic acid. So this is going to be 0.5 molar. I don't care about the water. That's not going to be part of my calculations. It's a pure liquid. Now, like when we were doing these problems in chapter 14, the products were always 0. But now you have some acetate ion. Initially, I can put this water or the hydronium in as 0. We don't have any of that in my list of major species, but I do have acetate, same molarity, 0.5 molar. Okay, so now the nice thing too is I don't have to do a Q because I know that at equilibrium I have to have some of that hydronium ion. It's got to go forward at least to some extent. So we can call that X. It's all 1-to-1 ratios, plus X plus X. So that at equilibrium, this will be 0.5 minus X, X, and 0.5 plus X. So you can kind of guess where we're going from here. We want to solve for X. They give me the K value up there, Ka. So it's an acidic buffer solution if they give you a Ka value. 1.8 times 10 to the negative fifth. Products over reactants. X times 0.5 plus X. And then on the bottom, I'll have 0.5 minus X. This K value is small, so you can totally 5% rule this thing. And actually, this ends up being really nice. Yeah, we're going to go forward, but probably not by much. So this original hydrogen acetate, that's going to go down slightly. And the final acetate ion, that'll only go up slightly. Get rid of both of them. Because now, how nice is this? X is 1.8 times 10 to the negative fifth. Convenient. And typical. That'll happen a lot. So now again, if I want to calculate the pH, the ion that I'm really concerned with, this guy. On the product side, both particles could affect the pH. The acetate ion is weakly basic. That hydronium is strongly acidic. Or if you would have written it without the water, you would have just had hydrogen ions in there. That's strongly acidic. So of the two products, it's the hydrogen or hydronium that really has the bigger effect on the pH. So I can just take this thing, pH equals opposite log of 1.8 times 10 to the negative fifth. That is like the hydrogen or hydronium concentration. Plug it in your calculator, you're good to go. This should be about 4.74. Cool. There's pH of a buffer. It's not bad. You just have two particles and 1 0. But you're still shifting it. You're still solving it for X. You can still use the 5% rule. Not bad. Okay, so now let's get to the meat and potatoes of buffers. Let's figure out what happens if we add some hydrogen or hydroxide to this thing. Okay. So we're going to add 0.01 moles of solid sodium hydroxide to a liter of that same buffer solution, the one that we just calculated. We want to know the change in pH. Okay, so when you write this equation, I think sometimes this is the worst part. You got to start with hydroxide on the reactant side, and the particle that'll react with the hydroxide. So if hydroxide is a base, I'm going to add it to the acidic particle in the buffer. The acidic particle in the buffer is the weak acid, acetic acid. O2 plus hydroxide. This is the particle that can react with the hydroxide. And then I ask myself, what's going to happen? Well, this acetic acid can give up its hydrogen. We'll form the weakly basic acetate ion and just some water. All right, we're going to ice table this thing. ICE. What do we have? Well, the original buffer is 0.5 molar acetic acid, and it's 0.5 molar acetate ion. I'll put the 0 in there. We can kind of ignore this water over here, so I'll get rid of that right away. It's pure liquid. And now we have 0 zeros. We have some hydroxide, 0.01 moles per liter. So that's kind of like 0.01 molar. Okay, so sometimes I call this like the buffer stoichiometry. Buffer stoich. Or you could call this the BS if you wanted to. We need to react this as completely as possible. So we're going to try to get rid of that hydroxide. That's kind of the point of a buffer. We want to get rid of this strong base so that at equilibrium, this guy goes down to 0. So everything else is going to shift accordingly. So it's 1-to-1 ratios. This guy's going to go down by that same amount. So that at equilibrium, this will be 0.49. Then we're going to shift this forward. The acetate ion's going to go up, 0.01. So that at equilibrium, this will be 0.51 molar. Now again, like here's kind of our trade-off. We got rid of all that strong hydroxide, strong base ion. The trade-off is we have a little bit extra acetate. Well, the acetate ion is weakly basic. So this should have a smaller effect on my overall pH than having a whole bunch of hydroxide swimming around. All right, so now we need to find the pH. After you do this buffer stoichiometry, I guess, that's kind of what it is. You're going to react these as completely as possible until that strong base is down to 0. Now let's calculate the pH. All right. So what I have left is still a buffer solution. And again, you could write this however you want. There's a couple options when writing the equation. You can leave the water out. You can put it in. If you left it out, you'd write something that looks like this. The hydroxide is gone. So we're going to have some of this hydrogen acetate. We're going to have some of the weak acid. It has the ability to dissociate, form hydrogen and acetate ions. O2 minus. Your other option would have been like you could put the water in the reactant side, and then on the product side you would have hydronium H3O+. Your math is going to be the same either way, so whatever you're more comfortable with is fine. So now we set up another ice table. ICE. What did I have? After I took care of the hydroxide, my concentrations changed a little bit. Now the acetic acid is 0.49 molar. We don't have any hydrogen, so this will be 0. The acetate ion went up just a little bit, 0.51 molar. So again, we can't have any zeros. This original acetic acid is going to dissociate a small extent. This is going to go down. The products will go up. So at equilibrium, I'll have 0.49 minus x, and 0.51 plus x. All right, we just got to solve this thing for x. They give me the K value in the previous question. Ka was, I think, 1.8 times 10 to the negative fifth. And so again, things look similar, but they shifted just a little bit. Products over reactants. X times 0.51 plus X. And on the bottom, I'll have 0.49 minus X. You can still 5% rule this thing. You can get rid of both X's. Now you just got to do a little bit of work to solve for X. It's not quite as convenient as the first time. But still, this isn't too bad. When I plug this in my calculator for X, I get about 1.73 times 10 to the negative fifth. And again, the particle that I'm really concerned with is that hydrogen. Or if you would have put water in, it would have been hydronium. Same thing. We can calculate the pH. Opposite law. 1.73 times 10 to the negative fifth. Hydrogen, hydronium, same thing. This ends up being about 4.76. Okay, so now interesting, the original pH that we calculated before was about 4.74, I think. Okay, so we just added some strong base. Somebody threw in strong base sodium hydroxide pellets. Yeah, the pH went up, but ever so slightly. That's how a buffer works. We traded that strong base for a little bit of weak base. We formed some extra acetate ions, but it barely changed the pH. Yes, it went up, but not by much. The other thing that's kind of interesting, we can compare this to what would have happened if we threw that sodium hydroxide in water. If we had 0.01 moles of solid sodium hydroxide added to just a liter of water, it would have basically been like a 0.01 molar sodium hydroxide solution. So it might be easiest to go POH equals opposite log of this 0.01 molar hydroxide solution. And the POH is 2. So if I subtract that from 14, the pH is 12. Okay, well, the original pH of water would have been 7. So by adding that same amount of sodium hydroxide to pure water, the pH changes 5 units. Adding it to a buffer solution, we barely noticed a change.